Okay, so we're just going through problems. So these ones, the dam. Okay, wait. So these are pretty straightforward. I know how to do these. Um, the dam one. The only thing to remember is that when you're finding the line of action, you have to take the moment about some point, and the moment you have to make sure that you include this water pressure moment, and that's the only thing that maybe tripped me up. Is I was like, do you include it? Do you not include it? But you definitely include it. All right, now we're gonna do this one because it's in the answer key. So let's see. Should I do it like this? I don't know. Okay, so uh, like that. We need this. This actually goes lower, like this, and then this is here is Z, Y, and then this has to be X, right? Okay. And then all the dimensions. Oh, God, this sucks. Okay, we got to get fast at this. So this is 60, 60, 50, 50, and then 10. And then here, this comes around. Bring it around town. And this is like this. This is a 10. This radius is a 40. Wait, do you have my mic on? I feel like I probably didn't put it on. Did I put it on? Oh, I did. Okay. 40, 10, 10, 60, oh, and then this 30. Okay, so wait. So we're going to... All right, let's just do this. Shape 1. And we're going to cut this. I'm going to have to remember how to do this. But we're going to cut this here. This is 2. This is 3. This is 4. And this is 5. And 5 is negative. Now the problem says find COG of y in the y direction. So we're trying to find, where along this axis is. So I believe that really all this is going to be is sum of mass I, or really volume. It's going to be volume I. It doesn't matter because it gets quotient out. Volume I times watt I over the sum of the volumes. All right. So shape 1 is going to be a rectangle. It's going to be 60 times 120 times 10. So this is V1. Now Y1, this Y will be minus 5. 2. V2 is this shape. It's this semicircle, and so we have to go to, I think actually the last class. A7. So it's this. So it's going to be 4r over 3 pi. So this is going to be 60. So wait, we're looking for the, this is for y2.
I forgot Mariana's here, so I'm not going to go to the store.
Okay. It's a crisis. Okay, so we have 4r over 3 pi. So it's going to be 60. Wait, no, y. I don't know why I'm trying to find x. We're finding y. This is also going to be just minus 5. And then the volume of this is going to be 10 times pi r squared over 2. So is equal to this radius has to be 60. This outer radius has to be 60 because of this line. Okay, so it's going to be 10 times pi times 60 squared over 2, so this goes to 5. Okay, so that's volume 2. 3 is this, the y component, so first V3 is going to be equal to pi r squared, so pi times 40 squared, pi r squared times 10, and that's the whole volume. Then y3 is going to be 5. 4. 4 will have a center y component of minus 50. And V4 will be 10 times 100 times 120. Okay, and then V5 is going to be minus pi r squared L. So it's going to be minus 10 times pi times 30 squared. And then Y5 is going to be the center of mass of this thing should be minus 50 also. Okay, so now we just need to apply this formula. Alright, so let's write this out. So 1, 2, 3, 4, 5. So we're going to get VI, YI, VI, YI. Okay, so 60 times 120 times 10, 7,200. Okay, minus 5. Minus 5. We can fill this one out because these are easy. 5 minus 50. Wait. Minus 5. Minus 5. 5 minus 50 minus 50. Okay, now we're going to get 10 times pi. Oh, shoot. Ooh, where did I put the marker? Oh. Okay. So, we're calculating. Okay, so 10 times pi times 60 squared divided by 2. Five, 6, 500. Okay, now we're gonna get pi times 40 squared times 10. 5,300. Wait, that. Okay, maybe. Alright, now 10 times 100 times 120. 120,000. And then 5 is minus 10 times pi times 30 squared. Minus 28,300. Alright, now let's do these products. 7,200 times minus 5. Minus 3,600. 36,000. Okay. 5, 6, 500 times minus 5. Minus 282, 500. 50300 times 5. 251, 500. Okay, 120,000 times minus 50 is equal to minus 6 E6, which is 1, 2, 3, 4, 5, 6. Then minus 28,300 times minus 50. This is positive. 1415000. Okay, now we just add these up. So the 36 plus 28 plus 251 plus the 6 plus this. Okay. Minus 465,200. And we divide this by this, which is what's the sum of this? 7,200 plus 5,6,500 plus 5,0300 plus 120,000 minus 28,300. 205,700. This divided by this, we get y bar is equal to minus 22.61. Let's see, did I get it right? That's the real question. No, I did not. What is wrong? I also did the orders wrong. We had 2 minus 50s, 2 minus 5s, and 1 plus 5. Okay, 120,000. 72. I think that this probably needed an extra 0. That needed an extra 0. So this needed an extra 0. Okay. Okay, good. Oh, but it is, yeah, it's minus. I don't know why she needed X. X, I don't think it makes any sense, but that's fine. Okay, so we're good with those. I'm good with those. I feel like the method is pretty simple. It's just easy to maybe get confused a little bit. Okay, so distributed loads, center of volumes, centroid of volumes. Did those. Let me keep it open. Okay. Okay, this one. This one I remember being pretty hard, actually. So method of joints is not going to be on it, but it's such a useful method that I'm gonna do at least the first one. Okay, so we have a triangle. Okay, we have a pin. Wait, is that a roller? This is a pin. This is a roller. There is a force here. What is the labels? A, B, C. $12, 3.75. This force is 945, and then this height is 9 feet. Pounds. Okay, so now, using method of joints, determine the force in each member. Okay. So whenever I see these problems, I always just start off, let's just take the whole thing as one system and draw the free body diagram. All right, so we have an external force here, we have an external force here, and then we have an external force here. So this is Bx, By, Cy, and then minus 945. Okay, so I think the easiest thing to do right now is to start off taking the moment about B. So we're going to get, this is 12, three-step row, this is negative, so we're going to get minus 12 times 945 plus 15.75 times Cy is equal to 0. So let me solve. Minus 12 times 945. Okay. Minus answer divided by 15.75. Okay, Cy is equal to 720 pounds upward plus J hat. Okay, so this becomes 720. Alright, so now we can do sum of Fy. So we're going to get By plus 720 minus 945 is equal to 0. So then we're going to get 945 minus 720. By equals 225. Okay, now we sum Fx and Bx equals 0. So then here we can rewrite this as 0. Bx equals 0. By equals 225. Cy equals 720, and we have the big things. So we have all the reaction forces. Now we want to find, let's say, the force in this member. So damn, I totally don't remember how you do these. if we look at this joint, we have this force on it, and then we're going to assume it's in tension. I always like to draw this drawing. So we have a beam that's in tension, so the force is pulling it apart. But that means that the joints are going in. So joints, mem, in, tension. So this is going this way. But then don't we also have this? I have no idea how you do these. What the hell? So you find the reaction forces, and then she looked at one of the joints, okay, and then drew a force triangle. How the hell do you draw? How do you draw a force triangle? How did she find that? Wait, AB is in compression? How does she find that AB is in compression? She guessed that it was in compression, but how else would you find that it's in compression? This is wrong. Okay, wait. If we draw this joint, the beam is exerting a force. Let's say that the joint is exerting force on the beam of 375 in tension. We're assuming, because we found the magnitude using the force triangle, but we don't know the direction. Let me just say that we find this angle. So A10 over 12. So now what we want is obviously this needs to then pull the So what we want is FAB times sine 36.9 plus 225 is equal to 0. So then we find that FAB is equal to minus 375. Which gives us FAB in C, compression. God damn. Alright, whatever. So, but we can apply the same logic here. So then that means that this force is 375 and this angle is 36.9. And so then what we want is that, 375, let's just say F minus FAB cos theta, cot theta, plus, now, because this is horizontal, we can just write FBC is equal to 0. So then we get minus 375 cos theta, and this is equal to FBC. So, and we assume tension because it's pulling in. So 375 times cos 36.9 is equal to 300. Tension. Okay, and now the last beam, the last member we need to do is A. So A, there's a joint here, 945, and then this way there's 375, and then here, and we know that this angle is 36.9, and so now we just have, this is going to be, we're assuming tension again. I always assume tension. This is going to be F AC. And so let's sum our forces in X, because that's the easiest. So what that's going to mean is that minus 375 sine, or let's say cos, can I just do that? Cos 36.9 plus FAC is equal to 0. Okay. I got 2 hours. Kind of. A floor truss is loaded as shown. Determine the force in members CF, EF, and EG. CF, EF, and EG. So they're telling you gotta cut here. So then we're gonna turn this into. So the first thing I want to do is find the reaction forces. I always want to do that. I don't care if it's extra work that I don't need to do. It makes me feel better if I know it. Okay. So what we're going to do is we're going to sum the reaction forces. And we're going to make the moment about K. So we're going to get 0.8. So this is a positive. 0.8 times 2 plus 1.6 times 2 plus 2.4 times 3 plus 3.2 times 4 plus 4 times 4 plus 4.8 times 2. So that's the torques due to these top forces about K. Then what we're going to do is minus 4.8 times AY. Okay, 0.8 times 2 plus 1.6 times 2 plus 2.4 times 3 plus 3.2 times 4 plus 4 times 4 plus 4.8 times 2 divided by 4.8. So AY is equal to 10.5 kilonewtons. Okay, then we can do the sum of Fy, and we're going to get, let's see, 2 plus 4 plus 4 plus 3 plus 2 plus 2 plus 1. So we're going to get minus 18 plus 10.5 plus Ky is equal to 0. So Ky equals 7.5 kilonewtons up. Okay, then we sum our forces in x, and we get that Kx equals 0. Now we can do the split. And we're going to split here. We're going to split on the left side. So what happens is we get this force, and this force. So I think the easiest one to do is we start off by taking the moments about E. So we're going to get, this is a 4 and this is a 2. E also has a 4 on it, but that doesn't matter for the moment. So we're going to get 0.8 times 4 plus 1.6 times 2. And this is 10.5 plus, or minus 10.5 times 1.6 plus 0.4 times CE. Alright, so 0.8 times 4 plus 1.6 times 2 minus 10.5 times 1.6. And we get minus 10.4 is equal to, 10.4 is equal to 0.4 CE. So divide this by 0.4. We get the FCE is equal to 26 kilonewtons of tension. So FCF. What are we trying to find? CF, EF, EG. Okay, now we can do our sum of forces about y. So first we're going to draw this triangle here like this. And we're going to get that this is 0.8. This is 0.4. So then this angle is a tan 1/2, which is common. 26.57 degrees. Now, the important part though is that if we sum our forces about y, we're going to get minus 2 minus 4 minus 4 plus 10.5 is equal to 0.5. Okay, so we have this vector. And so that vector FEF times sine, and this is a minus, I'm assuming it's a minus for tension, sine 26.6 plus 0.5 is equal to 0. So 0.5 divided by sine 26.6. And we got that FEF equals 1.12 kilonewtons of tension. Okay, then we can sum our forces in X. Oh my god, I hate this class. Okay. So summing the forces in X, basically we have 26 plus 1.12 times cos of 26.6 plus, and we're assuming it's in tension, so it's a, wait. Yeah, so it's a plus FEG. Alright, so I think that one's going to end up being in compression. But so 26 plus 1.12 cos 26.6. Okay, so I think that FEG is equal to minus 27 kilonewtons, which is equal to 27 kilonewtons of compression. Let's look at the answer. I think I got it, though. I think I did it. This is the first problem all day where I was like, okay, wait, maybe I know what's going on in this class. This one's easy. I don't want one of these ones with these crazy angles. I hate the trig. Trig is the worst part of this class, man. 27 compression, 1.2 tension, 26 tension. Let's go. All right, that one's not so bad. I can do that one. That one's pretty easy because you realize that the best thing to start out with is to take the moment about E, and that allows you to quickly find the cable tension or the force the force exerted by the member CE on the pin at C. I think that's the right way to say it. Low-key, my teacher's so nice, but like I like she's kind of like a robot. Like there's no passion or inspiration, man. Anyways, should we try this last one? I feel like method of sections probably will be on the exam. But the thing is, how much time do I have? Because there's also, like, I really should probably focus on a frame a machine problem. Okay, I think it'll be either a 1, 2, 3, 4, 5, 6. I mean, there's a lot of stuff she could ask, dude. All right, let's just think about the problem then. So we can definitely find these reaction forces, I think. So first off, immediately you sum forces in X and you get Kx is equal to 9 kips. Then you sum the moment about here and you get By. Then you sum on Y and you get Ky. Now you have all the reaction forces, and you're trying to determine the force in members AD, CD, and CE. So you cut here, and we're going to use probably just this tiny triangle, right? Do we want to use the big part or the little part? I can't tell. I think I'll probably take the big one. Because I don't know what to do about this little one. Like, because this little one is just this tiny triangle. And if you took the moments about C, then actually presumably, let's see, how does she do it? I think she probably takes the small one. Which one is this? 59. She takes the small one, then she starts with she finds the reaction forces, just like I said, then the moment, then Ky. Okay, so this is easy. Then she takes the moment about C, she does this part, then FAD, and she does minus, and then she goes 6.6 7.5. Okay. And the reason why you can ignore these two. Okay, all right. So actually that's pretty good. All right. That's pretty good. I'm just going to have to say that that's good enough. Because low-key, I'm not ready for this exam. This stuff is fine. This stuff is fine. This stuff is pretty fine. Frames and machines is actually, okay, this is definitely the right thing to be studying right now. Okay, so the main thing to remember here, to keep in mind, is two force members. 2 force members is the most important thing, I think, to keep in mind here. Alright, so let's try to do this thing. I think I can do this. I think I got it. Okay, so the first thing we do with frames, reaction forces. How many times do I have to say it? Reaction forces. Okay, so the first thing I'm going to do is so this is this is CX, CY, DY, and this is B, and this is A. So what I'm going to do is find the reaction forces. So first we're going to take the moment about C. And this is also a pin. This is DX. Okay, that's okay. So first we're going to get 12 times 90. Because this is a 2-4, actually, oh, but the reason is that because the pin is external, but the B is internal. You only ignore the force in BD if your free body diagram includes both members as one combined system. Yes. When solving for reaction forces, I keep it all as one. Right, okay. So, yeah, so I kept it as internal. But the pin itself is external. So we're going to do plus 4.5 times dy is equal to 0. And then we get minus 12 times 90 over 4.5. dy is equal to minus 240. So then cy is equal to 240. So then And then we also have that cx plus dx minus 90 is equal to 0. This is the sum of fx. And now, what we want to do is recognize that dy is actually a two-force member. So, because we can make this triangle, this height is 4.5 and this is 7.5. So then this angle theta is going to be a sine of 4.5 over 7.5, which is 36.9 degrees. Okay, so if we found that dy, so then we can also find that 7.5 squared minus 4.5 squared. Okay, so then this is a 6 here. So what we can do is we can use our law of sines to find that this force here in the force triangle, this is dy is minus 240. Okay, so what I think it's going to be is that $240. I think it's going to be 240 over 4.5 is equal to x over 7.5. So it's going to be 240 over 4.5 times 7.5. So I think that the force in BD is equal to 400. So now we can find and we assume that dy was actually negative. So this has to be going down. And since it's a two-force member, it has to be along the axis. So that means that the dx, so 240 divided by 4.5 times 6. Okay, so I think dx equals 320 positive. So then cy equals minus 320. Did I get it right? Did I get it right? 300. Wait. How did I get this wrong? Oh, yeah, because it is 6. It's not 4.5. I misread the thing. Okay, so this is actually 180. So then cy is minus 180. Or no. dy is minus 180. C is plus 180. So then this is going to be 180 over 4.5 times 7.5, which is 300. Okay. Alright, so the way that I did it is fine. The only thing is I just messed up the distance. All right. All right. So that one's pretty easy, and I feel pretty confident doing that one if I'm not careless. This one's harder, though. Okay, so first step is reaction forces. So we have an BX, a BY, we have an AX, and then we have the frame and F60. And so that means that we sum our forces in y, and we get that by is equal to 60 plus 60 j hat. Then we sum our forces in x, and we get that bx plus ax is equal to 0. Then let's sum our moments about b, and we're going to get that 8 ax, and then this is going to be 4 plus 12 is 16 plus 4 is 20. 20 minus 20 times 60 pounds is equal to 0. So then 20 times 60 is what, 1200 over 8. We're going to get that AX is 150 pounds. So that means that BX equals up minus 150 pounds. Alright, so the reaction forces have been solved for. And so now what we want to do is determine the components of all forces acting on member ABCD. Okay, look, so we have a pin here that's vertical. We have a pin here, and then we have a pin here, and then we have a roller here. So let's just draw, or actually let's draw it correctly. So BX is pulling away, minus 150. And BY is 60. Then AX equals 150, and then we have a pin here, CY and CX, and then we have DY. And so let's take our moments about C, I guess. So the moments about C, so this distance is going to be 4. So negative 4 times 60 minus 4 times 60. Then this distance from C to here is also 8. So it's going to be 8 times plus 8 times 150. Positive. Negative. And then D is positive as well. And that's a distance of 12. So this is going to be plus 12 dy is equal to 0. Okay, so it's going to be 8 times 150. Oh wait, this is going to be negative. There's going to be 240 minus 8 times 150 is equal to 12 dy. Alright, so 240 minus 8 times 150 divided by 12. dy is equal to minus 80 pounds. Okay, so now we can sum our forces in y. Okay, I actually feel like frame problems are not that bad. Yeah, frame problems are not as bad as I thought. I think I was just like, this one's actually good. I want to do this because I like frame problems. I feel like frame problems are like kind of fun. I hate all the other stuff, but frames are pretty interesting. Alright, so there's sum our forces in y, and we're going to get 60 minus 80 plus cy is equal to 0. So then cy is equal to 20. Then we sum our forces in x, and we get that cx equals 0. Let's see, did I get it right? Did I get it right? By is 60. Bx is 150 that way. Ax is 150 that way. D is... Oh, wait. Shoot. Wait, but did it say that? She would probably mark me down because I didn't write this. But I pretty much got it. Alright, let's do one machine problem then. It's 20 degrees. And we have a force Q here. How do you do this one? I don't remember how to do this. Okay, so the idea here is that there's 3 parts in the system. Yeah, there's this part, there's this part, and there's this part. So when there's 3 parts, you can actually just draw. I mean, there's actually 8 possible systems you could define, but just take each individual free body diagram for each part. And we think about it. We have this thing, we have a pin, and then a horizontal force. And I don't know what this internal horizontal hole I don't know what that means. I don't know what that means. And then so it's going to be 188. But now, this force is going down. So yeah, it's 188 times 33 over 250 of BD. Okay, that's correct. Okay, so the steps with this problem were draw FBD of each individual member. And in or wait, CE? CA. Oh yeah, because she just drew this without the... No, wait, what? I don't know. Oh, the hole? Oh. Yeah, so the linear bearing basically is what applies the horizontal constraint of the part. All right, so I'm good on that. Oh shoot, I have the birds thing due and I have the pre-lab. Oh, I have 2 pre-labs due tomorrow. I guess I'll just do them before class. That's fine. That's fine. Birds. All right. So let me just make a reminder. Okay. pin at B is attached to the member ABC and can slide freely along the slot cut in the fixed plate, neglecting the effect of friction. Determine the couple M required to hold the system in equilibrium. Okay. And there's 100 newtons down here. No, 25 pounds. Okay, so the idea is, let's just consider the free body diagram of AC, ABC. I'm gonna skip physics again today. I got to. Okay, so, but that's not even important. The important part is that we have Cy and Cx. So sum the forces in y, and we see that Cy equals 25 pounds. Then sum the forces in. Then we take our moment about y, or about c, and we get that, what is the length of this? This is 5.2. We're going to get 5.2 bx. That's minus 5.2 bx. Then the length of this is going to be 16 times cos 60, which is 8. 16 times cos 60. So we have plus 8 times 25 is equal to 0. So we're going to get 25 times 8 over 5.2 is equal to bx is equal to 38.46 pounds. So that means that Cx equals minus 38.46 pounds. But that's not even that important. What's important, though, is that here we have this 3 inches. And we have this thing. 6 inches, 8 inches, 3 inches. This is C. Basically, all we need to do is take the moment about D. So now we have system equals CD. And we take the moment about D. And so we're going to get M plus, and so it's going to be, so we need this distance. So we're going to get, so this angle here is A sine 3/8. So this is equals 22 degrees. So then Cx is positive, or Cy is positive 25. Cx is like this. So 3 times 25 minus, and then now we need 8 times cos 20, or we can actually, and we get 7.42. So minus 7.42 times 38.46 is equal to 0. So 75 minus answer times 38.46. So then I think M is equal to 210.2 what? Pound inches. Did I get it right? Bro, low-key, I feel like I did. Oh, she didn't even do this one? Let's see if I got it right. Where's my Ferdinand? Ferdinand. Which problem was this? 6.13. 6. Okay. Wait, I did it wrong again. Hold on. Let me think about this. I did it wrong in the same way I did it wrong last time. And I don't understand. Okay, look. Let me think about this. So, the force the pin makes on the beam but if instead it was like I don't understand, dude. So on the member ABC, the force points the moment from the horizontal force C is going to be damn, I made that mistake a second time. It's so easy to forget about that. You have to flip the sign of the force when you cross a pin. Okay. I gotta take a break. Okay. Should I do this one? How do we do this one? So first off, the alpha equals 0, 1 is pretty easy because this force is to the right. So then we get okay, let's do it. Wow, I'm like really not motivated right now. Okay, so B, this is B, this is D, this is A, this is C, this is A. So if we just consider B, D, B, C, then 1200 plus BX plus CX equals 0. And this is the fx equation. Then fy, we get that cy is equal to 0. And then if we take moments about c, we're going to get 700 times 1200 minus 500, because this is 100. 500 plus bx times bx is equal to 0. Then we get 700 times 1200 divided by 500. So bx, so wait, this is negative, so this goes over, this is positive. So bx actually is this way. Is that true? Because you're going to get this. Yeah, so Bx equals minus 1680 newtons. So that means that 1200 minus 1680 plus Cx is equal to 0. So Cx is equal to minus 1200. 480. Alright, so we have the reaction forces, and what are we trying to even find? Determine the couple M that must be applied to the crank AB to hold the mechanism in equilibrium. Okay, so what we need to do is basically say, alright, we have this member AB. Now we know that this force is 1680 and this is 100. So then the couple is just going to be 168,000, which is 168 Newton meters. And I'm pretty sure that's right because I remember that number. Yeah. Okay. Oh God. Oh gosh. Oh, I'm sore. Okay. I can't wait for the weekend. I can't wait for the weekend. I can't wait for tomorrow to be over. All right, I mean, I have like 3 hours left, so let's lock in. Cause all right, so I feel like I kind of know how to do some of these. Let's go to internal. Okay, this is the stuff that was new to me. This is where I really stopped paying attention in class. Okay, so wait, I have the answers to the loading. So I can use these numbers. And the idea is that we cut at J. Determine the internal forces, so axial force, which is F, shearing force, which is V, and bending moment, which is M, at point J of the structure indicated. All right, so low-key, I'm just gonna like look at her answers for. So for internal forces, what is the method again? It's like you cut it, okay, and that's it. You cut it, and then you find that there's a down. You already know from solving the problem. This will definitely be on the exam because it combines multiple things. So not only do you have to like solve for reaction forces and solve a frame problem, but then you also need to apply beam logic. So I feel like this is going to be on the exam. So the idea here is you cut it, and you can pick the simpler one that allows you to be like, okay, well, the shear force is going to be 80, the axial force is 0, and then the moment J is going to be some M minus 80 times 6. So then, okay, so that's it. That's a pretty deal to me. That's a pretty deal to me, boy. Okay, so yeah. So okay, this stuff is like not that hard. I feel like this one's pretty hard though. Maybe we'll do this one because you have to like. I guess this does make sense. If you cut this here, then all you have is this abstract. And okay, so wait, the weight is pulling it down this way. So why is the force going this way? All right, let's do this whole problem. I'm going to do this whole problem. So we have a beam with a roller, then a pulley, and a pulley, and this goes like this to a pin, and so this force is 600 newtons, this is 300 millimeters, 200 millimeters, 200 millimeters, the radius of this 120 millimeters, and then this last part is 300 millimeters. This is point A, B, C, D, E. Okay, so step one, oh, and we have a pin here. Right, because it's as if, like, imagine two guys are holding on to the two ends of the thing. It's basically, there's no net vertical force, but there is a moment created, and that's the result. And so this distance, so we're going to do it from here. So step 1 is we're going to take the moment about E. And so this distance is going to be 300 minus 120 is equal to 180. So we're going to get minus 180 times 600. And then here it's going to be 300 plus 200 plus 200 plus 120 is equal to 820. So we're going to get 820 plus 820 times 600 plus, this is going to be minus, actually. It's going to be minus 1 times AX, AY is equal to 0. So 820 times 600 minus 120 times 600, or 180 times 600. Oh, this is a 1,000. Divided by 1,000. Okay, so then AY is equal to 384 newtons. So now we can sum our forces about Y and get EY. So we're going to get EY equals minus 384 newtons. EX equals 0. Okay, so we solve for the reaction forces, and now what we want to know is, knowing the radius, determine the internal forces at point C. Okay, so now we're going to cut this thing. Alright, so C is going to have an axial force F, a shear force V, and a moment force M. So I think actually this is not going to be so bad. So what we want to do is, let's just find this angle as theta is equal to the arctan of 120 over 200. It's the radius over that section, and this is going to be 31 degrees. So now what I want to do is 600 newtons times sine of answer. Of answer. And we're going to get that that this is 308.7. And this newtons. And then we're going to get 600 cos degrees. And we're going to get 514.5 newtons. And now we can sum about our forces. So let's sum the y forces. So we're going to get 384 minus 600. So what I don't understand is the direction of this thing. I mean, I know she said I guess the direction is the other way. So then it's going to be minus 308.7 plus V is equal to 0. Okay, 384 minus 600 minus 308.7. So then V is equal to 523.5 0.7, and then F so F is equal to minus 514.5 newtons, so this way. Now we just need the moment. So the moment is going to be M of C. So it's going to be M plus, what is this? This is going to be 320 times 600. Then it's going to be plus 200 times 30 plus 200 times 308.7. And then for the sideways one, it's going to be a negative. It's going to be minus 120 times 514.5. And then we have one last one, which is going to be 500 minus 500 times 384. Alright, I think that's all of it. So 320 times 600 plus 200 times 308.7. God, this is so lame, dude. So I got the M is equal to 0. Please be right, please be right, please be right. Okay, so we got EX equals 0. We got AY is equal to 384 up. EY equals 384 down. F, the axial force. Oh yeah. Oh yeah. And then V is 525, 524. Yeah, that's fine. And then I got that the moment is literally 0. But she wrote this, but I think it's 0. I think there's no moment. Because she wrote the same stuff I did, right? Wait, 384? Where's the number 384 coming from? Oh, yeah, 384 times 500 plus 600 times 320 plus 308 times 200. Yeah, it's 0. It's 0, man. Okay. I'm actually pretty good on that, I think. I feel like those aren't that hard. The loading diagram, the main thing to remember is if you have a distributed load, okay, she didn't ever give anyone where this distributed load is like non-uniform. So if she does that, I'm going to be annoyed. Because what does that mean? That means that the slope... Because if you have a... Wait. Because if you are looking at the shear force diagram, if you're looking at the shear diagram and you have a distributed load and you're going across as you vary x, then if the load is distributed uniform, then the slope on the shear diagram will be linear. But if the... Okay, hold on. If I have a uniform distributed load, then the slope of the shear diagram will be linear, right? What if the distributed load is not non-uniform, but varies linearly? The change in the shear with respect to x is equal to minus okay. Let's do a problem. 7.35. Okay, so it's going to be at minus 15 in 0 to 1. Then it's going to be minus 40 in 1 to 1.3. Then it's going to be minus 10 in 1.3 to 1.7. Then it's going to be minus 30 in 1.7 to 2.5. So what we're doing is usually no. The standard convention is still to let x increase left to right along the beam even if the support wall is on the right. Okay, so we're just going to let x equal to 0 be here. So we're going to call this x equal to 0. Alright, so it's going to be at minus 15, then it's going to go down, then it's going to go up a little bit, and then it's going to go down again, and then it's going to go up. Let's see, is that the answer? Down, up, okay. That's pretty cool! Bruh. I want to be done with this quarter, man. This stuff's not interesting. I saw a friend's linear algebra exam prep, and it was like proving this abstract function is linear, finding its kernel, stuff like that. Like, I miss doing that stuff. I feel like that's way cooler. I haven't done math in so long, bro. I miss doing math, man. I need to find a good book for the summer that I could try to work through. I think I should still work through Algebra Chapter 0. But Algebra Chapter 0 is hard. Like, that's a very challenging math book. She'll probably want to see all this though. But okay, so the moment is important, right? So if there's a force at minus 15 here, then this is V. But then M will go linearly to minus 15 because it goes to 1. And then with a slope of minus 25, with a slope of minus 40, so this is slope minus 15. And this slope is minus 40, and it'll go only for 0.3. And then it decreases less suddenly, and then more suddenly. So it should just be like, yeah. And then when it hits the wall, it goes back up to 0. So how do you do this one? Is there a wall there? There's no wall there. So first you have to do the whole thing where 2 times 1.2, right? There we go. 2 times 1.2. But this is for the moment, so then it's applied at the middle. Dude, these things are so boring. Oh my god. I should probably do these cable problems. Catenary is not on there. We're getting some rays, taking a little break.